So welcome to our webinar today on design forecasting, which is our third webinar in this module on design forecasting. As you join, just listen in and you can jump forward, Jakob, please. And here you see the participant list for today. So we have quite a lot of participants registered. So we hope that most of them will show up, and it is covering quite a large part of the world also. So that is fun to see. So you can jump forward. And if you're new to this, for those that have been attending several webinars, you will hear this again and again. But for the newcomers, just to mention, this is a project called WebLearn, where we deliver webinars towards the metal and polymer component manufacturing industry, which can be seen as short, effective competence development, preparing the industry to be more or better ready once the pandemic is over. And as we all hope and see also, the pandemic is hopefully towards an end. We can take the next one. And me speaking is the one to the right. That is Stefan Berlin. I'm working with external relations here at the School of Engineering at Jönköping University. And the one to the left is Ehsan Gassamalar, who's the project manager of the WebLearn project. You will meet him at the end of the webinar today. But the most important persons of today are our speakers. That is Jakob Olofsson, working here at the School of Engineering, and also Magnus Wessén, actually also working at the School of Engineering, but more or less an industrial guest of today, I would say. It will be very interesting to listen to you today. And the format of today, we will just have this short intro, and I will hand over to Jakob for starting the presentations, and then we will end with a panel discussion before we wrap up in 1.5 hours. So it will be pretty effective, and please take part in the panel discussion towards the end. And if you're unfamiliar with our format, please have your microphones turned off since we are recording it, unless you are the presenter. And if you have questions during the presentation, do write them in the chat and we will address those questions. And please take part in the panel discussion towards the end. And as I said pretty early, maybe not all of you were here then, the webinar is recorded and will be available to you afterwards. So unless you are prepared to be seen by others, do keep your camera turned off. You can skip to the next one. And if you're unfamiliar, down to the left, you have the microphone on off, you have the camera on off, and a bit to the right, you can open the chat function box, and you can open that one and write a question. And do write the questions to everyone in that case. So we will note them, whoever it is noting it. It might be me, Jakob, or Magnus. So by that, I hand over to Jakob and for starting the presentation, and welcome again, everyone. Thank you.
Thank you, Stefan, for this introduction, and welcome all of you to this webinar. It's great to see so many of you here. This is, Stefan mentioned, our third webinar in this series called Design Forecasting, where we have put the emphasis on different aspects of casting and its impact on the design of cast components. And today we're having the topic of, which is Let's Do casting simulations, or DOE casting simulations. So today we have me, Jakob Olofsson. I am an associate professor here at the School of Engineering, I'm also working a lot with simulations and modeling aspects of casting. My background is as an industrial designer, working with design aspects of the different parts and castings originally. And then I stepped into the academic world again, came back from industry and worked with more with the casting simulations and development of that and different areas of that. And today I'm now teaching and doing research here at the School of Engineering, among others, teaching about design of experiments to students at different levels. And we also have our guest, Magnus Wessén, which I like to welcome also here. Please tell us something about yourself, Magnus.
Okay, so I'm a metallurgist. I made my PhD in '97 in working with cast irons, and then after that I worked with as a teacher at university in Jönköping for honestly I still work. I'm linked to university to a very small extent in my life, but I've also always been working with casting simulations. So after my PhD, I worked with development of the magma iron part of Magmasoft. Modeled the phase transformation, such things, and then nowadays I'm since 12 years the agent for Magma in Scandinavia or Nordic countries. So doing teaching, sales, support, training, all these things about casting simulation. So that's my main task. But I said also weekly linked to university as a little bit of support and some project at university. But basically, it's Magmasoft is my work today.
So today, Magnus and I are going to talk about design of experiments and with a special application to casting simulations. So I'm going to start with around 25 minutes, maybe, with talking about design of experiments. What is it? Why should we use it? Or why do we use it? I like to make this introduction to bring you into some important design of experiments concepts, and one of these that we will talk about is the full factorial designs versus fractional factorial designs, because that will kind of show us why design of experiments is quite an important tool to use. And for the second part of this webinar, Magnus will show us how this can be applied in casting simulations and how it's implemented, how we can use this to learn more about our casting process. And then we will open up for a panel discussion. If you have questions during the presentation, please write in the chat as mentioned. And when we switch here between me and Magnus, you will also get a link to a Padlet where you can start writing and preparing questions for the panel discussion later. So I will then start off a bit by talking about what is design of experiments. Well, I went to the source of all truths, all now internationally accepted, namely Wikipedia, to check what this is. And it says that this is design of experiments is the design of any task that aims to describe and explain the variation of information under conditions that are hypothesized to reflect the variation. And loosely interpreted, if we try to understand it, it's how we choose to change some variables that we think have an impact on an output, and how we interpret the variation in the output. So basically what design of experiments is that we are looking at some kind of process. It can be a process that we know how it works, or we don't know how it works. We try to understand this process by giving it an input. So we give it a value or an input, and then we check what is the output. So given one input, we get one output. If we then try again, we do give it another input, and then we get another output. So what we do with design of experience is to try to understand what happens now when I change the input, and how does my input change the output. If we're going to start from really scratch and try to give an example of what DOE can be about, it can be about understanding how does the freezing temperature of water vary with sugar content. Let's say we want to investigate that. So we make a test. We first try what is the freezing temperature without sugar. We do the experiment, we measure or do the analysis of this process and find that the temperature is 0 degrees Celsius. Then we try another experiment. We do with a sugar content of 50%, and we will see what is the temperature then. And somewhere about -5 degrees. So we can actually see that there is a relation between the sugar content and the output, the temperature. So starting with some basic concepts of DOE, this would be that we have some output, and it's called a response, because that's the response that we get out from the process. In this case, the example, it's the freezing temperature. We have what is called the design variables, and that is the input variables that we can change and that we think affects the response. So in this case, the sugar content was the design variable. And then we have what is called the design space, and that is the region or range in which the design variables are allowed to vary. In this case, we vary the sugar content from 0 to 50%. So that's our design space that we are investigating. So this is basically what DOE is about. Why should we use this? Well, don't we usually do this? I mean, it's about working in a smart way. Yeah, it is. And one could say that DOE is doing this in a structured way, in a methodological way. It's a methodology to gain as much useful information as possible. And I will come back to this useful information later. It's also a way that helps us understand complex processes with many variables and responses. So it's a way of handling these many design variables interactions in a smart way. And when we talk about DOE and the why to use it, there are kind of DOE is different things depending on what you want to do. And you typically talk about 3 different types of main objectives. The first is called screening. So that is that you're interested in finding the most significant design variables. Because in a complex process, you can have many things that changes. But when you do screening of this, you want to find the most important ones that really has an impact on your output. Then we have what is called optimization. And that means that you want to find the point within this design space that has the best response value. The third objective is called robustness. And that means you want to find a region in this design space where you have a good value of the response, but the response also is stable. And because optimal and robust does not have to mean the same thing. If we, for example, look at this response here, we have a change in the design variable. Well, the best value would be if we are here. That's the nominal optimal point. But if we just have a small change in our design variable, you can see that we will have a different, very drastic change in our output. Instead, you might be interested in finding a robust optimal, where you have a very good response, but it's also stable. You know that you don't have too much changes if you have slight changes in your design variable. One of the strengths of using DOE is, as I said, that we can handle multiple variables. And that is typically what you do as a human. You do handle a lot of multiple variables. For example, let's say you want to buy a car. This is also an example where you do work kind of methodological, even though you may not even think about it. You can say that one of your design variables, that can be the price. the price of the car is something that you are considering, but you are probably also considering other aspects as the size. So that can be one design variable. And when it comes to price, well, unfortunately, we cannot always afford the fancy cars. So we do have a limitation. We have a maximum price that we are able or willing to pay, but often we also have kind of a minimal price. I mean, we don't want to buy too old, or if it's too cheap, you might get suspicious also. And similar as when it comes to size. And this means that you are actually defining a design space. This is the region of interest that you have, in which you are willing to find your car. And by searching through this design space, investigating, looking at different brands, different colors, and so then you will finally find, hopefully, your choice of car. When we want to transfer this into the world of casting then, well, in casting, we do have a lot of design variables. So it's easy to come up with a lot of things that can vary if you look at your design and manufacturing process. For example, the geometry of the casting. You can, as a designer, you can probably think of different ways of designing your part. The chemical composition, something that typically varies in a real production. The ingate system, you can probably think of different ways of having your ingate in different ways. Your mold design, where to put your feeders, what pouring temperature should I use, etc. It's many design variables that you can think of. And then we have this casting process that gives us some kind of output. And the responses that we might be interested in, it might be very different. It might be properties. You want to reach a certain yield strength in an area. It can be that you're interested in reducing the porosity or maximizing the yield, reduce or remove hotspots. Part price can even be something also, or many other things that we can think of. So how can we use casting simulation? Well, this is a really powerful tool that we can use to explore our design space and see what happens when we have a certain set of design variables. We can do a simulation and get our response. And similarly here, we can define our design space. We can pick a point, we insert our values of the design variables, we do a simulation, get a response value or a response in some way. 3D distribution of things, or what it is we're looking for. And we can repeat this several times to get our responses at many points in our design space and understand how our process is affected by our changes in our design variables. And this is really powerful, but the real beauty of DOE and design of experiments comes when we start talking about how to use this for having multiple variables of things that can change. And because the interesting thing is here is, as you know, simulations takes a lot of time, takes a lot of the computational power, and we really want to do this in a smart way. So the question is, how can we explore our design space using as few experiments or simulations as possible to get as much useful information as possible? And to start looking into that, I have to actually start talking about mathematics as well, and understanding what it is that we get out of this in a more systematical way. So I want to talk about a regression model. And what is a regression model? Again, according to Wikipedia, this is a function that describes the relationship between one or more variables and a response. So basically, it's about quantifying how do we interpret the effect of our change in our variable on the response. And today, I'm mostly going to talk about this from the point of view of screening, because talking about multiple variables. And for screening, it's very suitable to use kind of a linear model where you have your response, in this case, y, and we choose a regression model to describe this output, how it's affected by our variables. So we have a constant term plus a factor multiplied with the first design variable, plus a factor multiplied by the second, and adding up, continuing to add for the other design variables that you have, plus epsilon, which is an error. So we don't really need to focus on that today. And this is a linear model, but then we also have interactions between some of these design variables. For example, if you change chemical composition, maybe you change your silicon content, then it will have an effect. But if you change both your silicon and your copper content, it will have a different effect than adding just changing one of them. So that's why we also will have these interaction terms to consider, where these design variables are multiplied with each other. There are also more advanced models that we could use, for example, for optimization. You can have a quadratic model, but we're not going to talk too much about that today. Instead, we're going to focus on this, and especially I would like to highlight these interactions that we will return to later. So one very straightforward way of working this is that we do a full factorial design. So what that means is that each variable has a high and a low value. This is called a two-level full factorial design, because each design variable has a low and a high value, just these two levels. And then we run all these combinations. So marking this, we have x1 is low and x2 is low. That means that we're at this point and we get our response. Then we move to this point where x1 is the high value and x2 is the low value, and we get the response here. And then we move around at these 4 points. So we try all the possible combinations, which can be quite useful for screening of variables. It also supports these interaction models. So we also will understand the interaction between those parameters, because you can see we are changing them independently. We are changing x1, then we're changing x2, and then we're changing them together to get to that point. This is very straightforward, gives you relatively few fronts per factor and gives you quite a lot of information. But what happens if we increase the number of the variables, or in this case, then we get more factors? Well, let's say we have 3 variables, 3 factors that we change. That means that we will need 8 experiments. So looking at this graphically, it would be a cube in a 3-dimensional space. So we are changing x1, we're changing x3 in that direction, and x2. And looking at the combinations now, we can see that we need to then do 8 experiments to get all this out. And the more factors we add, we will get into what is called a hypercube, where we have, it's hard to draw this graphically when you get into multiple dimensions, but it's called a hypercube of k dimensions if you have then k factors. And these full factorial designs, they are good in some ways because they do estimate the interaction models. So we get a lot of information, and we investigate the factor at both levels of all the other factors. So they are assessed independently, which is called a balanced and orthogonal experiments. The con, however, is that the number of experiments increases dramatically, as we will see. Then this is really the cost of this basic approach, because as we have more variables, let's say we have 4 variables that we can vary, well, then we need to do 16 experiments. If we have 5, 32, and as I said, we can easily find many variables in our casting process. So let's say we have 7 factors that we can vary. That means that we would need to do 128 experiments or simulations to get all this information. But what is it then that you get out of this? Well, I said we had to run 128 simulations. That also means that we get 128 model parameters. So looking at our regression model, it looks like this. It's you first have the constant term, you have the basic variables, and then you have all the two-factor interactions. And then you have all the three-factor interactions, x1 times x2 times x3, etc., until you have all the seven-factor interaction. So we have one constant term, we have 7 linear terms, but we also estimate 121 interactions, where 21 of them are two-factor, 35 three-factor, etc., etc. And are all of these really useful? Well, some of them are. You can see again the interactions here. The constant term, that is something we really do want. We do want to see, when we talk about screening, we do want to see which ones are the important variables. So we want the linear terms, and we also could be good to see if there are some two-factor interactions. The three-factor interactions, these are typically very rare. Yeah, so typically you will here end up with these factors being 0. And when it comes to the higher order interactions, we are not really interested in them, because usually you don't have 4-factor or higher factor interactions. So typically this is all 0. So about of your 128 experiments, the data that you get, the 128 model parameters, yeah, half or more will be 0. And that we can say already from the beginning. So at least every other experiment that we do is actually waste. So we're getting a lot of information, but half of it is not even useful or relevant. We could already have told you that it would be 0. So here comes the real beauty of designing experiments, that you want to do this in a smart way. So you only do the useful experiments and get the useful information. And one quite straightforward way of doing this is to use the fractional factorial designs instead. So we talked about full factorial. That means that you're looking at all the points, but if half the amount of simulations are useless, then maybe we can only take 1/2 of this. And by picking them in a smart way, we still keep it balanced. It means that we are changing the variables in a smart way, so we still can get useful information. We can take these 4 experiments. Let's say we take these 2, 3, and 5, and 8 instead. It's still balanced around the center of this cube. This is the first fraction you can consider, but you could also, of course, take the other one, the other fraction, number 1, 4, 6, and 7. It will still be balanced around the center of the cube. And the beauty is when you look at higher order, when you have more factors, then you can reduce this even more. And you write this fractional factorial designs with us in this format. 2 raised to 3 means that it's a 2-level factorial design with 3 variables. And here, if you add -1, it means that you have cut it once. If you look at 5 or more factors, it's a 2 raised to 5 full factorial, which means that we have 32 corners. But if you cut it once, we add -1, we have 2 fractions with 16 experiments each. And if we write like this, 2, 5-2, that means that we have cut it twice. So we have 4 fractions with 8 experiments, and they are still balanced around the center of this hypercube now. So we're only doing half the amount of experiments and still getting the useful information out of this. But what's the price we pay for this? I mean, this doesn't come for free. We do lose something, right? And that is called confounding. What does that mean? Well, it means that we are getting a bit confused now, because the factor effects are to a certain degree mixed up with each other numerically. So they can no longer be computed independently. For example, if we look at this, we have 4 variables, and we cut this once. So we look at 1/2 of the experiments. That means that we will have a confounding pattern that the constant term is actually confounded with the 4-factor interaction. And the factor for the single variables is confounded with the 3-factor interactions. So we cannot really say if the value that we see, is it because of this factor or is it because of this combination of factors? But if we look at this numerically, what you will find is that, okay, the 3-factor interaction is typically quite small compared to the actual factor. So when it comes to screening, it's enough to know that, okay, this is the most important factor. Then we do have a small confounding with the 3-factor interaction, but it's enough to say that, okay, we think we can find that this is a more important factor. But this confounding, it is the price that we have to pay. And how much you can pay of this? Well, it depends on your purpose of your setup, your experiments. And how we measure this is called design resolution. And basically, the higher the design resolution, the less confounding. So the more similar we are to a full factorial design. And if we have, this is measured by the resolution number. And if we have a resolution which is 5 or higher, that means that even our 2-factor interactions are unconfounded. So this is almost as good as a full factorial. We don't not producing much waste. If we are going down to a resolution of 4, that means that our main effects are unconfounded. So this can be useful for screening. We can find the most important variables. But our 2-factor interactions are starting to be confounded. So it's hard to say, to quantify our combined effect of changing our variables. So this is what is recommended for screening, because it's a good balance between the number of factors and the number of experiments. If we are starting to cut too much in these factorial designs, then our resolution will be 3 or lower. Then our main effects are confounded with 2-factor interactions. And this is really complex. And it's not something we want to do in screening, but it can be useful if you're talking about robustness, which is another topic. So what we end up with is a resolution sheet where we can show that, okay, depending on how many number of factors, we need a certain number of runs. So if we have 3 factors, we need 8 runs to do a full factorial. If we just do half of them, 4, then we're in the red, we're in the resolution 3. So this is not good for screening. So if you have 3 variables, okay, 8 simulations or experiments, that's good. That's you can use. But if you have 4 factors, okay, that means that you will need 16 to do a full factorial, but doing 8 experiments, well, you still have enough information to do screening. So it's you just need to do 8 simulations again to investigate 4 factors. And as the number of factors increases, let's say we have 7. Well, if we do 128 experiments, we will do a full factorial. That means that we have a lot of information, but for screening, we can cut it once, twice, and even 3 times. So with 16 experiments, we can still investigate 7 in factors and do screening. So to understand our complex processes, where we have many things changing, we can actually use fractional factorials in a very efficient way to find which are the most important variables. Then we can go into detail and analyze those factors in more detail. There is much more to say about this, and there are many even more smart ways of picking your experiments. For example, the different algorithms to find your points in the design space. A Sobol algorithm, there are methods called D-optimal or I-optimal and different approaches to this that you could talk much more about. And also, we have not even mentioned about optimization and robustness. And there is much more to say about this. But these are the basic theory I wanted to cover today and show you a bit about, to understand that, okay, design of experiments is about doing your analysis in a smart way. And fractional factorial can be a good way of doing that. And full factorial, if you have not so many variables, but if you have many variables that are changing, do consider to use a fractional factorial. And design of experiments is then something that can be integrated in your workflow. And this is where I want to hand over to Magnus to show a bit more about how this can be applied in the world of casting simulations and how this can be integrated. So Magnus, I hope that you're still with us.
Yes, I'm here.
The camera is still working also, or is it?
Yes, it's working. So I will just share my screen.
I don't see you on the here.
Once you have to see me as well, but I will allow that in a minute. Okay.
Just a second. I will just also here in the chat, I will now put a link to a Padlet where you already can go in and start writing questions that you have to me or to Magnus that we will bring up to the panel discussion afterwards here. So now you have a link here in the chat to the Padlet where you can write your questions. So Magnus, please.
Great. You see my screen now, I suppose?
Yes, it looks good.
Okay, so thanks for a nice academic background to using DOEs and so on, but I will be more practical in this. I will give a few cases where I demonstrate how we can use design experiments to for casting processes and casting optimization. That's my short topic for today. The first thing, you can think of DOEs, you can use it for to achieve robust production. That's one thing. In a foundry, you think of normally you have to find a robust production. But from from designer's perspective, you have something. About the robust design, you have to design something which is easy to cast, and so you can make sure that you really get the good parts every time, even if you use different foundries. So if you have a good design from starting point, you will make it easier for the founder to make a robust production. So I think there is use of optimization both for the founders and for the designers as well. But just as an example, this is imagine this is some quality criteria. It could be the porosity, it could be the hardness, something. You have another criterion here, and then you have some operating point. It could be, this is how the foundry is running their process, and the most days it works fine. So you're staying below this line. So you have a good, enough quality, both qualities criteria are fulfilled. But sometimes you have a high humidity in there, or it's melted too cool that something happens, then you get out of this. So that means that now you're not really having a robust production. So sometimes you get bad parts. That's what we need to achieve. So you have to find the process and tune your process that you can find some spot in design space where you always get good parts in production. And so that's the topic. Many people today, people use casting simulation to optimize the process in a manual way. And quite often you're not really in a safe spot. You're not really safe that so. Many founders know that certain days you get bad parts. So I will just show some simple cases. So in this very first simple case, I will just explain how we can use the set of DOEs to optimize this part. This is a cast iron bracket, which has, say we can have been delivered by the designer. And it's, if you make a very simple rough simulation, first of all, if you just make this solidification simulation, you can easily identify that there are one big hotspot here, long solidification time, null hotspot here. And then you have some smaller hotspots. That means, of course, if for this cast iron part, especially if it's ductile iron part, which shrinks more than gray iron, you can expect that there will be some porosities here, and also maybe up here if you're unlucky. Unless the founder finds a way to produce it without it. But the problem is that this part, this area is not easy to feed. You would need a feeder here maybe, or on the side here, not easy to place. So this part is easy to feed from this area. And then, of course, the problem is how to do that in a smart way. I mean, so the best way would be if the designer already from starting point could find a way to take away this hotspot so that the foundry gets the part. This is already removed. There's only one big hotspot that can be fed from one location. But most cases, this is not the situation. So then the founder needs to find some tricks to make it work. So I will now just go through this case and we can discuss it afterwards if there's some questions. I mean, so in the first case, this to make this work, I mean, the founder had designed some gating system, a feeder, and they couldn't find a way to remove the process in this very critical area. They had to add some padding material, and hopefully the designer or the casting buyer could accept this padding material to create, I mean, direction solidification. This is what you have to do. I mean, so the target of this manual optimization was to add some material so that you could get the direction solidification all the way from the feeder into the part, so that you have good feeding and you can avoid the process. And this is what achieved. So this is ductile iron 500. This was poured at 1330 and using, so we can say, default settings in the program. And this is what most people do. I mean, they use the standard settings, optimize something to get it look nice. I mean, here you don't see any porosities in this area. This is the critical area. But then, of course, the question is this something which we can rely on for production, and also it should work in all cases whenever something happens in the production in the process. So of course you can then easily set up by extremely small amount of work. You can in the program in Microsoft you can go into what is called the optimization perspective. If you have designed your part, you have, I mean, this you have maybe a CAD pro with the CAD and the mesh and everything is set up. You can easily go into the optimization perspective. And then you can tell what are your design variables, what are varying in the process. I mean, for instance, this case, the foundry from the first flask to the last flask, if you're making several pourings from a ladle, might vary maybe 60 degrees. So then I said, okay, let's try what happens if we run from instead of 1330, which was my target and good pouring temperature. What happens if I go down to 1300 or up to 1600, 1360 in steps of say 30? So that means 3 simulations. But then the other things which can happen in processes as well. I mean, certain days you have a worse metal quality. If you have more oxides, for instance, dross slags, those can nucleate porosities. So that means that your shrinkage tendency gets higher. And in Magna, we have something called the shrinkage potential factor, which account for this without explaining the details. I mean, so you can easily then say, what happens if I go away from the normal setting to high and then low and see how that would affect the situation. Also, the inoculation, which do, I mean, to promote the graphite formation, that will affect the shrinkage. It's another factor which is quite important. You can then easily also add those two. So then you have 3 levels of the temperature, 3 levels of the metallurgical quality, shrinkage potential, and 2 levels of the inoculation. So now you have directly 3 times 3 times 2. That means 18 possible designs. Of course, this is done, say, with 2 minutes extra work. Just go in here and select your parameter, which are varying, and then create your start sequence. And in this case, it's a full factorial design. You can also do reduced factorials and fractional factorials, but in this case, I will only discuss full factorial designs. And of course, then you have to think, what are your objectives? I mean, what you would like to achieve. So in this case, we know that this was the critical area. So what I then did in the geometry perspective, or in the CAD part of the program, I just included small box. And that box is what I call an evaluation area. So I would like to, my objective is to reduce the porosity in this volume, within this volume inside the part. So I can then say, I would like to, at the end of solidification, I want to have my weighted volume, which is basically the total pore area, inside the casting, which is also inside my evaluation area. So this will be a result telling me the pore size in cubic millimeters in this volume and how that is affected by these parameter changes. Again, so this done in a few minutes work, and then I get out lots of information. And as you know, I showed in the first slide that this was a good simulation. I didn't see any porosities, but now when I play around with these designs, I can see that there are actually 4 designs where I get some porosity. And of course, you can manually start to analyze the numbers. You can see that, for instance, if I have a low, say 1300 and 1330 degrees, same here, together with a high shrinkage potential, then it seems that I get some porosity. Then you can start analyzing this way, but you also have some evaluation tools. We have, for instance, what's called the main effect matrix. Then you can directly see that for this case, I mean, this is not always the case, but in this particular area, you can see that when we increase the pouring temperature, the porosity goes down. So we have a negative correlation, quite strong negative correlation, meaning that when this goes up, this goes down. The inoculation also has a similar trend, but very weak. It's not very strong effect. And of course, this is the metallurgy, or the shrinkage potential has also very strong correlation. So directly from this simulation, you can see we are not in in robust place in the design space. We cannot make sure that we always produce good parts. So then, of course, what to do? Then you have to do something to make this work. And then I simply, I mean, this is the typical way to do things. I mean, if you cannot break it, this was the original design where I added 40 cubic centimeter of extra material to make a direction solidification. That was quite good, but not good enough. And then if you make a manual optimization in this first round of simulations, I mean, just added a larger volume, tried it out. And then I added something which was 32 cubic centimeters, did a new simulation, and then it worked. So then that's one way to do things in a more manual way, but still using DOEs. Already at this stage, I actually could have drawn some conclusion only, instead of running all these 18, I could actually have made it even more simple, since I knew that the highest pouring temperature is good and the lowest pouring temperature was the bad one. So I could use this number and that number and that number. I mean, the settings, all these 3 settings would be enough just to try it out and to find if this is good enough. But now, of course, it shows that all my designs produce good parts. But it was an even smarter way. I mean, again, this could be from a designer's perspective. They would like to do this by themselves before sending part to the foundry. They could optimize the geometry. I mean, if you in this part, this padding material was designed as a surface which I was rotating around this axis. Then I can define this extra volume or this padding volume by radius 1, this height here, and the radius 2, and the position of this point. So I can shift this point in this direction. And in this way, you can, of course, you set up this with the worst case scenario. I mean, I will now use it. So now I will create lots of new designs, but then I will only run it with the worst pouring temperature, the worst inoculation, the worst shrinkage potential. And if you do that, you get out, I don't remember how many optimization I run, but I run now from 14 to 20 millimeter for radius 1, 12 to 16 radius 2, and the position from 90 to 110. And then you can analyze it in what we call the parallel coordinates diagram. Then if I just can drag these points, and then if say I only accept the solutions where I don't have any porosity, you can directly see the combination of parameters which yields some good results. In this case, so this is the volume of my padding material, which is now something like 20. And that is the best solution, the lowest volume and still getting 0 porosity. So now I have to say, okay, I'm quite happy. I have reduced I have a more robust process. I don't get any problems at any time. Even for the worst parameter settings in the foundry. But the question is, of course, if this is the best optimum or the robust best optimum which I can have. But then if you evaluate this main effect diagrams again, you can see that I mean, yeah, these are quite obvious. So when you increase this, the radii, process goes down and the padding goes up. That's clear. But you can also see that when I mean, arbitrarily chosen values on my point goes whenever I go in this direction, the process goes up. But it also means that maybe if I could have even better solution if I go even lower. So this is not, I haven't found the best optimum. So then you can easily, of course, I could have selected a larger design space for this one from the beginning, but then that would increase the number of simulation quite significantly. Then it's maybe better to do this in sequence instead. So then, of course, you should try same things with lower values for this one. I did set up a new one where I went from 10 to 14, slightly lower values, 10 to 12, 14 here, 65 to 85 instead of from 90 to 110. And then we can see that there's one design, actually only one design, which is now at 75 millimeter location for this point, where I actually had no porosities. And the good thing is now that now actually we have found something which is I mean, the trend is that this value seems to be where we really minimize the porosity. So it's most likely this optimum location, more or less. It may be 68 or something, but roughly this location. And we have found out, I mean, a design which has given me 17 cubic centimeters instead of 14, which was the initial design. Now, by only increasing the padding material with a few percents, we can really define the design which is robust with respect to all the variation in the foundry. Okay, so this is quite a simple example from how we can use it to find the process optimization and also for the design optimization for the for designers work. But then I will show some other more cases from the foundry. Let's see, time is it? We have some time. So this optimization for some classical feeding optimization in the foundry. This is a planetary carrier where, I mean, the founder have to find some tricks to make this good in production, robust production. And of course, what they have done, they have played around with the padding on the shaft, this padding or the draft angle here, some feeders on the top, some cooling chills at the bottom, and some cooling chills at the shaft. So of course, there are lots of ways to create direction solidification. I mean, you need to have a start solidification down here and make it go up and feed from the feeder. And then, of course, how to do that manually takes some time. So of course, in this case, it's quite simple to set up the feeder variation. You have this variation in this radius or this shaft, different configuration of your chills, and also different feeder sizes. And then the output is quite simple. I mean, you can see they have defined some evaluation area, which means they check the porosity in some location and seen that whenever, I mean, the best results were obtained with the highest impact from the chills. And easily you can find out when you have this kind of chill configuration, whatever the other parameters are varying, they're still in a very low and safe range. Because this is one quite simple case to find out which is the most important factors, and then to design your part to get a robust production. Next case is slightly more complicated, I would say. This is a case where the foundry had problems with trapped air, or some cold shut problems and trapped air in this location. So if this is the recasting, and here you see the air pressure as opposed in the simulation, and you can see that this is a cold area. So when the melt fills up, this gets quite cold. So that's a risk cold flows here, and you have this trapped air process problems. So then the object of this one was run a number of virtual experiments to identify the root cause of this problem. And there are many things which can affect this. So now, the matrix can get more ugly. I mean, we have the carbon content has an impact on the liquidus temperature, so that could affect the cold shot problems. The same with the silicon. And those things can vary, so then play around with that in 2 levels. Of course, also pouring temperature has a big impact, of course, for the cold flows. So that could vary as well. And then there's something called the graphite precipitation. I will not go into detail, but that's related to the shrinkage, we can say. And then another thing which varies in the process often is, I mean, the pouring cup level. How you feel melt in your pouring cup. I mean, that's depends on the skills of the foundry man or the how you program your robot and I mean the pouring machine in some sense. So those things can vary, but also sometimes you have a good compaction, sometimes you have the worst compaction, so you could also have different permeability in your sand. So now you have much more, again, it's only running on 2 levels, but now you have 64 possible combinations. And they run this simulation in full factorial. And then that could illustrate the results in this way. I mean, here you have the pouring temperature variations. You can see if you use a higher pouring temperature, quite safe. I mean, at least for this variation, the pouring temperature, big impact. The tendency to go to cool shots. With the pouring cap degree has also quite a big impact. I mean, these are not huge impact, but still they have quite big. So if you're running this high pouring cap, you have a much higher lightness to get good results in terms of cold shot problems. But then again, you have this the main effect matrix. You can actually, if you evaluate the air entrapment problems, that's most affected by the pouring cap filling degree, which has the slight highest impacts. If you run with a bad filling degree in your pouring cup, you will entrain more air in the melt probably. You have more swirling in downspool. That causes problems in production. So you can then illustrate or analyze the results in many different ways. I mean, this is just showing on the blue axis, you have this tendency of air entrapment. These are the different designs. On this yellow axis or orange axis, you have this tendency of cool shots. You can see that, for instance, there are quite many experiments where you have a big tendency for air entrapment. So here you have lots of trapped air. These designs 12, 26, and 5, for instance. Then you have a few of them which really gives a really bad risk, a high risk for cold shots. And then, of course, there are some good designs as well. Here you can find some, at least 2 or 3 designs where have both low risk for cold shots and low risk for air entrapment. So that this is simple screening of the running 64 simulations without doing too much analysis. You can find out something which will improve your production. Okay, I think we have time for another case.
Can I just interrupt with one question around that?
Please. Please.
Because here you showed us you had 6 factors at 2 levels, so that means 64 combinations.
Yeah.
And still, when you go to the results, 2 slides ahead, I think.
Yeah.
You move. Or next one, there one.
Yeah.
You can see that it is one factor that kind of dominates the really shows. I think this could be interesting because I think this would be an interesting example of using a fractional factorial could be useful.
I agree.
Because here, if looking at back to this resolution chart I showed you, it probably could have used just 16 simulations to get the same, identify the same factor.
I 100% agree. I mean, this is the most cases people do in this way. I mean, it's simple to do the full factorial if you have a powerful computer. But if you really get to many factors, I mean, you should do it in that way. And especially as you start thinking. I mean, sometimes you shouldn't do too many things. And normally you should first start thinking about the parameters which are important and don't throw in everything. So then you will have problems to analyze anyhow. I think, I mean, so I agree. I mean, in this case, I definitely think it should be better to use a fractional factorial.
That was interesting too.
Yeah, good point.
You see.
I have to say these are quite old cases. I didn't run them myself either, so I cannot blame, should not blame anyone. But I think, I mean, it shows on the potential of using how to run it. Another case which is fun, and this is combining a little bit of porosity and the mechanical properties. I mean, this is brake discs and how you orient your brake discs in your with respect to in relation to your gating system and your feeders, you will have variation in properties. I mean, the feeders will cool the part more slow during your technical transformation. That means you have lower strength. So in this case, I mean, the foundry was trying to find out the most optimum design of the gating and the feeding to minimize or minimize the amount of porosity, and also to minimize the variation hardness inside the brake disc. I mean, if you have a hard area here and a soft area here, that will cause vibration, other things. So this is a nice case where you mix really two different kind of objectives which are not related to each other, but it's good to find what is the best design. So here you can see all the possible designs, 36 designs. And of course, these are, I would say, not parametric. These are really different. Yeah, it's not easy to find the interaction of these, how to you design your gate. So you have to, I think you have to run full factorial, that's my guess. And in this plot, you see, I mean, the output values, or I mean, they have defined the difference in hardness on this axis, and this the minimum, or the total pore content. I mean, so there are lots of dots here, and each dot is one simulation. So you have the design number 7, 11, and 3, which are the most. I mean, you have to design by yourself. This one has an even lower porosity content than that one. But you have to make your own choice which is the best one, or should I use that one? Because that has lower variation. You have, but these are the, yeah, then we can call the Pareto line of designs which could give interesting results. And then this shows the design number 7, which was, I think, maybe the smartest solution. You still have some porosities, but this should be at least this minimum porosity. Most you have the minimum variation in the hardness. It's the hardness, paralytic hardness for this great cast iron disc. So in this way, they could find both minimize, reduced porosity as well as the hardness variation. Okay, I think Jakob, can I have 3 more minutes, or I take it? So this is final example. This is about the stress formation in a huge gray cast iron machine bed, where they, during machining, found out they get quite high stresses in this location. And the stress are caused, of course, I mean, you're releasing stress when you're machining vein material, but also the stresses comes from the cooling. So if you can control the cooling of the part during the casting, you could, how to design the cooling such that you minimize the stress formation during cooling and also machining later on them. So then what was done, I mean, they tried to cool the part in this problematic area by introducing chills. And that was done in this way. They made a chill to, I mean, so they take away more heat during cooling, and they could vary the thickness of the chill, the width of the chill, but also the position, so that you can move it around in different locations. I don't know in detail how that was done, but I mean, you have some position here, you have the thickness, the width, and you have the stresses. Then you can, again, you can simply drag this line, find out the ones where you have the most low residual stress. And from beginning with us, you could have 208, and even you can get out 150 megapascals in the residual stress of the machining. This is, again, a very simple case where you can, instead of playing around by manual optimization, you can do quite a small number of extra work. You can get quite much more information to reduce the problem of cracking when you do the machining. Yeah, I think we skip here. I think so. We leave time for questions. I think if that's fine with you, Jakob, I think I stop here for now.
Yeah, these are some good examples, and I think it's good that we take some time to invite for some questions. Yeah. Very interesting examples, and I think it shows both how to use it for geometrical design, as you showed in the beginning, how to design for casting. I mean, and they really use the power of DOE to find a good solution, which is both lightweight, reducing the amount of material, but also making a pore-free material in the production. So you're actually preparing the part for production designing for casting, hands-on. Really. And there are some questions I like to address. Let's see. There was first one on the Padlet here. The first question was there, how do I define design resolution, and how can I decide which factor should I avoid for the simulation? Yeah, that's a good question. I'll see if I can again share my screen. I will go back to a slightly expanding what I showed you before when we talked about confounding. So I hope you can see my screen there now. What does it cost? We talked about confounding and confounding patterns, and I showed you this picture about which graphically shows how the factors are numerically distributed here. So how to get to the design resolution? It's actually what you do is that you have you're looking at three concepts. There is something called the design generator, the defining relation, and that will then lead you to the design resolution. And just briefly trying to explain these, the design generator, it shows you how these factors are numerically related now when we have done this fractional factorial. So if we look at, for the first fractional factorial here that we had, taking experiments 2, 3, 5, and 8, what we see is that they are numerically related, because if we take minus and minus, we end up with a low value of both variables. We end up at the high value. But if we take the high and low, we end up at the lower value of x3. So we can see this as a multiplication. Minus times minus becomes plus, plus times minus is minus, minus times plus is negative times a positive value is a negative value, and two positive values are multiplied, also becomes a positive value. So the generator here can be formulated as x3 equals x1 times x2. If we're looking at the other half, we will actually change the order here. So we will have minus would be something, we would look at the negative value of the x3, or the low value of x3. So that means that minus x3 is x1 times x2. And what and why we use that is to get what is called the defining relation. So what we do is that we identify these generators, then we take these and multiply both sides with the left side. And so here, this is the generator. X3 is x1 times x2. So what we get is x3 times x3 times is equal to x1, x2, x3. And that will give us the defining relation, because if we take this square, we have the identity column, if we're talking this in vector forms. So if you look, for example, look at the two-level factorial with 4 factors and cut it once, then the generator is x4 equal x1, x2, x3. If we then multiply both sides with left side, we get x4 squared, which equals x1, x2, x3, x4. And that means that the defining relation looks like this. And why is that useful? Yeah, because that is what reveals the design resolution. So the design resolution is the length of the shortest word in the defining relation. And if we go back to our example here, we have 4 terms here, which means that our design resolution is 4. So that is how we find our design resolution. And for this example, we have 5 factors and cut it twice. The defining relation looks like this. And the shortest possible word here would be 3. So the resolution is 3. And that is what gives us our design resolution. And this, as I showed you before. So the higher the resolution, the closer you are to a full factorial, getting as much as the information as possible.